everyone, we continue with the second part. In this part, we will talk about Ross theorem, mean value theorem, and also more absolute max min stuff. So let's continue with this problem, 67. Okay, so what we want to do? We want to show that this function has neither an absolute minimum nor an absolute maximum value on its natural domain. So, of course, for finding absolute maximum values, we always start with the same thing, find critical points. This is the function, and y prime. I am just applying derivation rules here, take the power down, subtract 1 from the power, similarly like that. This is our first derivative function. And let's search for where it is 0 and where it is undefined to find out the critical points. Look at the powers. These are even powers, right? So the values from the first and second expression may be at least 0. Since the powers are even, they are greater than or equal to 0. So even if they are both 0, we have this plus 1 here. You see, that's why the first derivative can never be 0. It is at least 1. So no point coming from here. No point. And as it is a polynomial, it is defined for all real numbers. There is no point where this polynomial is undefined because it has no denominator. It doesn't consist of any ln or square root function, so everything is fine. For all real numbers, this first derivative function is defined. Also from here, no point counts. So there is no critical point for this function. No critical point. But still, we want to find its absolute maximum values. What we should do, we should look at the domain endpoints. Just the endpoints we are left. So look at the function. What do you think is the domain of this function? As it is a polynomial, it is defined for all real numbers. So the domain of it is from minus infinity to plus infinity. In other words, the all real numbers. So our list consists of just the endpoints of your domain. Since domain is an open interval, we will be using limits to check the endpoints. As x goes to minus infinity, as x goes to plus infinity. Since there are no critical points, we have just these two in our list. Okay, let's look at the limits. Limit of the original function as x goes to infinity is, what do you think is this limit? You will just look at the dominating term, x to the power 11. So it is infinite. And now we will look at the limit as x goes to minus infinity. Since the power is odd, it is minus infinite, right? And since the values are, we obtain both plus and minus infinities, we will compute like there is no absolute max, there is no absolute min. Okay? No absolute min, no absolute max, and no absolute min values. So like this. I guess this solution is okay. Let's continue with 69. This one, this time, you see the function there, y equals 1 minus e to the power x divided by e to the power x plus 1. The question is the same. So we search for the absolute maximum values. That's why I will start with computing the critical points. So first derivative function. Since this is a quotient function, I will apply quotient rule. Derivative of the numerator is minus e to the power x times the denominator minus numerator stays the same times the derivative of the denominator divided by the square of the denominator automatically. This is what we call as the quotient rule while taking the derivative. Okay? If you do all the simplifications, you will end up with this compact form for the first derivative. Okay, e to the power x plus 1 square. Okay, let's try to understand where it is 0, where it is undefined. E to the power x function is always positive. Okay, it's a function which is always positive. And also here, the denominator as a whole is always positive because you are taking a square and e to the power x plus 1 is always positive. That's why if you try to understand y prime 0, you will find no point. No point coming from here. Is this first derivative function undefined at some point? Denominator never 0, so no point again. No critical point, but I want you to notice something. There is also this -2 coefficient there, right? So this makes the first derivative always negative because all the other parts are always positive because of this -2 coefficient. I can say that y prime is always negative. Okay? If now I will give you some information from next week. You can think it of as a spoiler of next week. So if the first derivative function is always negative, this tells you something important about its graph. If first derivative is always negative, your graph will be decreasing all the time. Okay? Then y is always decreasing. Okay? So remember what we were trying to do here. We were trying to detect the absolute maximum values of this function, and we find out that it is always decreasing. So and there are no critical points, so I should draw something like this, always decreasing. And as you can see from this graph, there is no absolute max because it keeps increasing, it keeps decreasing. So no absolute mean. Okay? And yeah, this graph is always decreasing. Okay, so we will use this kind of discussion in this case. Instead of saying that it's always decreasing and computing no absolute max mean, you can also look at the domain endpoints, minus infinity, plus infinity. Look at the limits. You will find, again, minus infinity and plus infinity as the limits. As in the previous case, you can also proceed like that, but I just want to show you a different perspective. Okay, if no questions, I want to move on. Now, we will start talking about mean value theorem and Ross theorem, starting from this example. This example wants us to find and prove something. Show that the given function has exactly one root in the given interval. So exactly one root, proving exactly one root requires to use Ross theorem. Let me put a recall for you. Do you remember that we covered intermediate value theorem in one of the previous weeks to prove a function has at least one root? Okay, to prove that f of x, a given function, has at least one root, we used this in the previous week. We will use intermediate value theorem, and to prove that a given function has exactly, not at least, but exactly one root, you need to use the content of this week, which is Ross theorem. Okay, so you need to remember this too. Exactly one root is proved by using Ross theorem. At least one root is proved by using intermediate value theorem. So now let's turn back to examples. A function is given tangent theta minus cotangent theta minus theta, and the interval is given like that. To prove exactly one root, you first need to prove that there is at least one root by intermediate value theorem, and then we will use Ross theorem to prove that it is exactly one. Okay, how do we use intermediate value theorem? First of all, you need to check its assumptions. To be able to use intermediate value theorem, your function has to be continuous. Okay, this is the assumption of theorem. To use it, you need to check the continuity of your function. Look at your function, please. Tangent theta, cotangent theta, they have some discontinuity points. Like, you know, tangent theta is sine over cosine. And cosine theta is 0 when theta is pi over 2, for example. Tangent theta is not discontinuous at pi over 2, but look at the interval. It is not included. So over this interval, we are safe. Tangent theta and cotangent theta are always defined. Okay, so I will remove this one. So over the given interval, tangent theta and cotangent theta is always continuous. So I will say that r theta is always continuous on the given interval. Okay, so this is checked. After checking the continuity, you can use the conclusion of intermediate value theorem, and let's recall that how it works. I will recall it geometrically so that you understand better. We are working over this interval, right? We will find a positive value of the given function r theta, and then a negative value of the given function, and to connect these 2 points, these 2 images, with a continuous graph, I have to cross x-axis. This is x-axis, so this point will be the root of this function. R of c will be the root then. So all I need to find out a positive and a negative value of this function. So to find where at which x value this negative value occurs, at which x value this positive value occurs, I mean these 2 x values, you need to find out that. You will do some trials and errors. So let's try some points. Of course, we will start trying by using the known angles like pi over 4, for example, which is in this interval. Okay, that's right. R of pi over 4. Tangent pi over 4 is 1. Minus cotangent pi over 4 is 1 minus pi over 4. So it is, these are cancelling. You see, we obtained a negative image. So I think this works. Pi over 4 works for the negative image. Now let's try another known angle. Over this interval, let's try pi over 3. I think there is no other known angle in this interval. Yes, pi over 3. Cotangent, tangent pi over 3 minus cotangent pi over 3 minus pi over 3. So it is kind of like this, square root 3 minus 1 over square root 3 minus pi over 3. And this value is positive value. Okay, we can discuss it at the break time why it is positive, but we have limited time. This is a positive value. So this angle was pi over 3. Okay, now I am ready to use the conclusion of the intermediate value theorem. By IVT, intermediate value theorem, there is at least one C such that f of C is 0. Okay, so that's it. We proved by intermediate value theorem that there exists at least one root. Now, the second part. I hope this part is understood. We first check the assumption here. If your function is not continuous, you can not use intermediate value theorem. It has to be continuous. It has to be checked. Yes, it is checked. Next, we find out a negative value. We find out a positive value. Then the conclusion follows like that. Okay, now how we will prove that? There is no other root. There is exactly one root. This conclusion is not enough. It says at least one root, but we want to compute that there exists exactly one root. To prove it, we will use Ross theorem, and we will use a new idea called proof by contradiction. So you need to listen to me carefully at this point. To prove there is exactly one root, we will use proof by contradiction. How it is applied. Okay, the fact is that this function has exactly one root, right? We know that this is a fact. But what would happen if there would be another root? We will assume this. We will try to analyze what happens, what would happen if there would be another root, and we will end up with a contradiction that if there would be another root, we would find something ridiculous, something that doesn't make sense, and this would prove that there has to be just one root. Okay, so we will assume to the fact contrary to the fact that there is another root. Okay, proof by contradiction works like this. So assume to the contrary that there is another root. Okay, let's call this root as C2 and let's call this one as C1. Okay, let's make it C1. So let's say there is another root C2 like this, and then now we were able to use Rolle's theorem. You know, Rolle's theorem. Should I remind the assumptions of the Rolle's theorem? Maybe I should. Okay. Rolle's theorem. You need to check things. First of all, f of x should be continuous over some closed interval. F of x should be differentiable. I think we have our interval, right? Let's use it. Differentiable on it. And there is one more thing. You need to have some equal images like this. You know, we assume that there is another root, both have input 0. All of these three assumptions should be check continuities, okay, right? And you know, r of theta, tangent theta, cotangent theta, we can compute its derivative, so it's differentiable over this interval. Differentiability is checked, and we also have these equal images. Then the conclusion is, now I will draw a picture and you will see the conclusion. What happens here? We have C1, we have C2, and for both of them, the image of our function is 0, right? They are roots. And I need to connect these 2 points with a continuous graph. So I need to have some turning back point. So it says that there is at least one number C, let's call it a C now, such that, what is special about this point? There is a horizontal tangent, right? Such that f of C is 0, exactly. No, pardon, I'm sorry. Okay, we were writing, yes, this part we were writing this. There's horizontal tangent here, so f of C is 0. This is the conclusion of Rolle's theorem, okay? So all the assumptions, after checking all the assumptions, this is the assumption box. The conclusion box is there is at least one C in your interval. By the way, I think I need to change these points to C1 and C2 because I use those notations. Okay, like that. Okay, because C here is between C1 and C2. That's why I am choosing the interval like that. C1, C2, such that its first derivative is 0. Okay. Now, this is not part of the solution. I'm just explaining the conclusion and assumptions of Rolle's theorem to you. But it makes sense, right? If you have these two equal images, there must be a turning point. And at that turning point, you have to have first derivative 0 because there is a horizontal tangent there. Okay, back to our example now. Okay, we are almost done. Now, we assume there is another one, there is another root, right? That's why we have this. With the second root, we have this. And by Rolle's theorem now, Rolle's theorem, we conclude that there is C between C1 and C2 such that F prime C is 0. But this can never happen. Remember that what we were trying to do. We assume there would be another root. But if there would be another root, we obtain this information which is totally wrong. That's why there cannot be another root. Now, I have to explain you why this is totally wrong. Because look at your function and look at its first derivative. By the way, can I change this f to r because r is the name of our function, you know? Okay, r of theta is given as tangent theta minus cotangent theta minus theta, right? It was like that. Yeah. Okay, let's compute its first derivative. Derivative of tangent is secant square theta. Derivative of cotangent is similarly cosecant square theta with an extra minus sign. So this becomes positive, -1. What is 1 over secant theta? It is 1 over cosine square theta. This is 1 over sine square theta, like that. And now consider what kind of values this first derivative function may have. This is less than or equal to 1 always, right? Also for this one, less than or equal to 1. Now 1 over something. Well, you are dividing 1 with some number less than 1. So this expression should be bigger than or equal to 1, right? Similarly, you are dividing 1 with something less than or equal to 1, so bigger than 1. And in total then, you have something bigger than 1, something bigger than 1, -1. So it is kind of 2 minus 1. So the smallest value of the first derivative is 1 then. 1 plus 1 minus 1, kind of. Okay, so the smallest value of this expression is 1. So it can never be 0. You should compare this to UC. So the first derivative function, the r prime theta, can never be 0, okay? So you should compare this to, you see, we obtain a contradiction. Or I can say that this contradicts with the fact that r prime theta is less than or equal to 1 always, okay? So what happens? We assume that there is another root. We assume to the contrary that there is another root. We did something, we used Rolle's theorem. I explained the details to you. And if there would be another root, we obtain this. But this is something totally wrong. Why? We understand here that over here, that we understand first derivative should be always bigger than or equal to 1. If there would be another root, we obtain this, which can never happen. So there cannot be another root, okay? This is the logic behind proof by contradiction. And if in your math exams or anywhere, if you are asked to prove that there is exactly one root, you will first use intermediate value theorem to find there is at least one root. And then you will use Rolle's theorem like that to prove that there cannot be another root, like we did in this solution, okay? So the overall conclusion is, so there cannot be another root, which proves that r theta has exactly one root, okay? If there would be another root, you obtain some contradiction. So there cannot be. In short, the logic is like that. Okay, to understand proof by contradictions may be a bit confusing at the first sight, but once you revise it by yourself, and once you remember my sentences, like if there would be another root, you obtain something ridiculous, you obtain some contradiction. So there cannot be. Okay, any questions about this solution, where we proved the given function has exactly one root? If no questions, I want to continue with the next example. Okay, let's continue with this one. This question, this problem is about mean value theorem, which is the remaining content of this week. Let's also cover it and then we will stop. Okay, I think I need to recall you the assumptions and conclusions of mean value theorem. Okay, mean value theorem. There are the assumptions and the conclusion of the mean value theorem is so similar to Rolle's theorem that I constructed here. In fact, the assumptions are the same. Rolle's theorem and mean value theorem have the same assumptions because Rolle's theorem is a particular case of mean value theorem. You will see, I will explain. So the general theorem is mean value theorem. For some particular case, it transforms to Rolle's theorem. So the assumptions are the same. Okay, f of x should be continuous over a closed interval, one of the assumptions. F of x should be differentiable over the same open interval. And these are the two assumptions. Then the conclusion. This is the assumption box. And now the conclusion box is, then there is a number C between A and B such that mean value theorem is about the first derivative function such that f of b minus f of a divided by b minus a. First derivative is given like this. Why I am telling you that Ross theorem is strongly related to mean value theorem? Because if you add one more assumption that f of b equals f of a, what happens to f prime c? If f of b and f of a is the same, what is f of c? 0 over something, right? 0. So you see, we obtain the conclusion of the Ross theorem. With this extra assumption, which is the third assumption of Ross theorem, remember? In Ross theorem, there is this third assumption with the equal images. The first two assumptions are the same. With this extra third assumption, mean value theorem becomes exactly the Ross theorem. So mean value theorem is the general case. Ross theorem is a particular case of it. Okay, after recalling those things to you, now we are ready to solve our example. Okay, it says, for this function to satisfy the assumptions of mean value theorem, find out the parameters. So assumptions of mean value theorem, as you can see, continuity and differentiability. So the given function should be continuous and differentiable over its given interval. By using these two information, we can solve for A, B, and M, the unknowns. So solution of the question. The given f must be, to satisfy the assumption of mean value theorem, must be continuous. Over which interval it is defined? You see, it is defined from 0 to 2. So we will use this interval. Must be continuous on 0 to 2, and it must be differentiable on the open interval. Okay, so let's use the information. Let's check continuity at 0, for example. Continuity at x equals 0. How do you check that? Remember, f of 0 should be the same as the limit of your function as x goes to 0. Let's see. What is f of 0? It is given as 3, right? F of 0 is 3. Now I will use, by the way, I need to approach from 0 from left, because from the interval, you know, from this direction, from left. Then I need to use this expression for the function. Minus x squared plus 3x plus 8. Minus x squared plus 3x plus 8. So just compute the limit. Just insert x equals 0. What do you obtain? If you insert x 0, you will just obtain a. So you see, we directly solve a equals 3 if you use continuity at 0. Now let's check another point for continuity. We can check 1, for example, continuity at 1, right? Okay. Continuity at x equals 1. This time I will look at one-sided limits if they are equal or not, because we have on each side of 1 we have a function expression, so we can check whether x goes to 1 from left, limit x goes to 1 from right, whether they are equal or not. So from left, as x is less than 1, you will use minus x squared plus 3x plus 8. Again, minus x squared plus 3x plus 8. From right, where x is bigger than 1, this time we will use mx plus b. Okay, so time to compute the limits. You will just insert x equals 1. By the way, we solve a as 3 above. So if you insert x equals 1, I think left-hand side becomes 5, right-hand side is m plus b. Okay, so far we find a and we find an equation including m and b. We haven't used the differentiability information. Now we can check f is differentiable at x equals 1. Let's check that. Differentiability at x equals 1. Remember, how do we check differentiability for one of the functions in the first lecture? Left-hand side derivative, right-hand side derivative should be the same. We use this idea once. Okay, so limit of, but this is the original function. We need to take the first derivative of it first. Okay, before checking these limits. Now, I am interested in the differentiability. That's why I need to write the first derivative function except the breaking points, okay? So, let me see. 0 to 1, 1 to 3. 0 to 1, 1 to 2. Between 0 and 1, we have this expression here. And I will take the derivative of it. This is a polynomial. We can easily take the derivative. So minus 2x plus 3, right? After you take the derivative. Minus 2x plus 3. Between 1 and 2, this time, look at here. Take the derivative. Just m. Yes, just m. Okay, and be careful. I didn't include x equals 1 anywhere. X equals 2. You see, the points where the definition changes should be all excluded. They need special attention. Remember what we did in the first lecture. So never include that. Yes, we already know that f is differentiable over here. It is differentiable at 1. But just to make sure and just to follow the standard way, I won't include it. Now, we are checking differentiability at 1. That means that we need to check left-hand side derivative, right-hand side derivative, whether they are the same in the limiting value or not, which we did before. Okay, differentiability at x equals 1 is checked like checking the limits of not the original function, but the first derivative from left, from right. Okay, now you have your first derivative function here. From left, you will use this expression, minus 2x plus 3. From right, you will use the other expression. Right? Now, just insert x equals 1 everywhere. So this is 1. Right-hand side is just constant m. You see, we find out the value of m as 1, and then you can easily solve for b because we have this equation coming from above, so b is solved as 1. Okay, we find all the parameters. A is 3, m is 1, b is 1. And the question was, let me remind you the question, for what values of a and b, this function satisfies the assumptions, hypothesis of mean value theorem. The assumptions were continuity and differentiability. So we use some continuity at 2 points and differentiability at 1 to solve for the values of the given unknown parameters. Okay? So like that, let me show you the solution as a whole. Any questions on this solution now? Okay, I will solve one more question. This question is about mean value theorem. So, some information is given like f of 0 is 5, and first derivative function is a constant function 2. This is given. The question is, must f of x be 2x plus 1 for all x? Give reasons for your answer. Okay. Yes. If first derivative function is given for all x, this means that f of x is differentiable for all x, right? It is differentiable given as 2 as a constant function. So from this sentence, I understand that just a second. F of x is differentiable for all x. Is that correct? F of x is differentiable for all x. Yes, correct, because the value is given as 2 for all x. Now, I am using a theorem. If a function is differentiable, it has to be continuous, okay? This is a theorem that we covered in our lecture videos. If it is differentiable, then it has to be continuous for all x. So, differentiability and continuity is checked. Because I want to use mean value theorem, that's why I need to check these two conditions. Now, they are checked. Then by mean value theorem, let's say apply mean value theorem on, we need to apply it on some interval AB, right? Now we will choose these AB points. Apply mean value theorem on 0x interval. You will understand why I could not just B, but x. You will understand it. Okay, let's apply this theorem on 0x interval. The conclusion is there is some number c between 0x, right? Such that f prime c is given as f of b minus f of a divided by b minus a. B is chosen as 0, x minus 0. Okay, this is the conclusion. And let's see what we can write. F of 0 is given as 5. This part is first derivative function is a constant function. No matter what value you inserted, it is always 0 as 2. Sorry, you see, it is a constant function, always 2. So what you have here then? 2 equals f of x minus 5 divided by x. Can you solve for f of x here? You can easily. F of x is 2x plus 5. You see, we obtained what we want. The question is, must f of x be like that? Yes. You see, applying mean value theorem, we find that f of x should be like that. Only with this expression, you can make sure that f of 0 is 5 and first derivative is a constant function too. Only with this expression you can. But you see, if you insert 0, you obtain 5. If you take the derivative, you obtain 2. Okay? So this is an application of mean value theorem. And one final example before I let you go. It is also not that long. It's the short one. Because these type of questions I see everywhere, I want to show you one example of that. Show that this inequality holds for all x values, okay? And there is a hint. Consider this function on this interval. We will apply mean value theorem on this function on this given interval to prove the given inequality. Okay. So we will apply mean value theorem. Apply mean value theorem for f of x given as cosine t on the given interval 0x. To apply it, we need to check first the assumptions, right? Let's check the assumption. Cosine t is continuous everywhere. So continuity is checked. What is the first derivative of it? Minus sine t. You see, we can take its derivative. So this function is also differentiable everywhere. Okay, continuity is checked. Differentiability is checked, which means that we can apply now mean value theorem on this interval, for example. So the conclusion is there is, I want to write all those things on the below part. Okay, so after checking the assumptions, now I can apply mean value theorem on this interval. So the conclusion is then there is a number c between 0 and x such that f prime of c is what? F of x minus f of 0 divided by x minus 0. I know what is f of x. It is cosine x, right? f of t is cosine t, so this is cosine x. What is f of 0? What is cosine 0? It is 1. So what we obtain here is, by the way, we also know the first derivative function. What is f prime of c? This is minus sine c. You know, the first derivative function is minus sine, so minus sine c. Okay, what we obtain from this equality is minus sine c is cosine x minus 1 divided by x. Okay, that is what we obtain. Now, I will take the absolute sign of both sides. Okay, you will understand why. Let's take absolute sign of both sides. Okay. You know, what is the biggest value of sine c? Maybe I should have written this equality on the other side. We obtain that this is equals minus sine c, and I put absolute sign. The biggest value of the absolute sign of sine function, no matter which angle you inserted, is 1. And then what happens? So you can distribute this absolute sign to the numerator and denominator separately. Am I right? Cosine x minus 1x is less than or equal to 1. And then this will be the final line. Let's make this. Okay, I took it down. Okay, and after this line, you can just multiply each side by absolute sign of x. Just get rid of the denominator. Multiply everywhere with absolute sign of x. So this is what we were trying to prove. You see, we proved it by using intermediate value theorem. Cosine x minus 1 in absolute sign is less than or equal to absolute sign of x. And the only tool here that we use is mean value theorem. To be able to use it, you need to check the assumptions of mean value theorem, which is continuity and differentiability. After these two conditions are checked, you can apply it over some interval. And then if you write the conclusion box, which is this equality, f prime of c is given like that, and the rest just follows. Okay, this is how you prove inequalities. Don't forget, if a question wants you to prove some inequality, like this type of questions, you need to consider applying mean value theorem. Okay, so that's it. Any questions? If no questions, I think that's all for today. Thank you for your attention.